Alright, second half of the video. This is part where we talk about torque and angular acceleration. Well, we said that torque was the, we said that torque was the rotational version of force. And we said that moment of inertia is the analog of mass. Okay. And that makes sense. Back in the day, we had the old force equals mass times acceleration, of course, Newton's second law. And we're going to have the same thing for rotation. Newton's second law for rotation is the same law, but it's going to use all of our new friends, all of our new rotational analogs. So it's going to be the sum of the torques equals I times the angular acceleration. Or as I think it was Marissa Bowman several years ago referred to it as torque equals I fish. I alpha is just fine though. Okay. I'm going to say torque equals I alpha a lot, but you can say I fish if it makes you happy. So the idea is that if we look at the units, we're going to have Newton meters for this, not joules. This is going to be kilogram meter squared, and this is going to be radians per second squared, which again, I listed as 1/second squared because radians is not a real unit for us. And a kilogram meter squared per second squared is exactly what a Newton meter is. So the units are going to work out swimmingly. And this actually is a pretty good deal. It lets us solve a lot of different things. Remember, it's the sum of the torques, and they all have to be about the same pivot point. That's important. All added torques are about the same pivot point. You can't choose, you can choose whatever pivot point you like, but they all have to be about that same pivot point. So be careful. Remember, if a force is at the pivot point, if the force is at the pivot point, its torque is going to be 0. So judicious placement of of the pivot point can actually help you forget or ignore forces that you don't know. I'm going to do one problem, and that problem is actually a problem you've done a bunch of times before, where you have a block on a pulley and another block hanging. This is going to be M1, this is going to be M2, but we're going to do something different this time. We're going to actually give the pulley a little bit of mass. So it's going to have a mass M, radius R. That's going to make it more difficult because now we're not going to be able to say that we actually have another thing that we have to include in our inertia. So if we look at the forces on it, if we look at the torques on this, torque is going to equal I fish. And the torque in this case is going to be whatever tensions are acting on this. So it's going to be the pull of these two. These won't be exactly the same. They won't balance out because they're going to turn the wheel also. So there's going to be some additional motion that we're going to have to consider. And that means that if we look at these, that the tension here and the tension here may or may not be the same. So we're going to have T2 minus T1 acting through R, the radius, is going to equal the moment of inertia. It's a cylinder, a solid cylinder, so it'd be 1/2 mr squared fish. That seems pretty complicated, okay, but it's not terrible, especially since we know lots of this stuff. And we can actually make the usual force diagrams for these. If I was looking at the M1, I would have tension 1 going this way. I'd have normal force going this way, and I'd have weight going this way. I'm going to say that the friction is 0 here, just to make our lives a little easier. So T1 is going to equal M1A. And if we look at the force diagram for the other, it's going to be T2 and M2G. This is M1G, sorry. And we know that so we know that T2 minus M2G is going to equal M2, and I'm going to call that negative A, because it's headed downward, the other one's headed to the right. So now we can actually solve for this stuff, because I'll have T2 equals negative M2A plus M2G, which means I can now put those back in here. I can say M1A. Oh, sorry. My fault. Actually, I can just move this over, can't I? I'm going to undo that, though. Okay. If I can move this over. No, I didn't want to do that. I can just say minus M1A, and it'll be M2G minus M2A times R equals 1/2 mr squared alpha. Well, so now this is known. But I have A and alpha, and how are they related? A equals R alpha, or R fish. So we can replace all of the A's with R alpha if we want, and just solve for what the angular acceleration is. So we'll have M2G minus M1 plus M2 R alpha. Oops, sorry. All times R equals 1/2 mr squared alpha. So let's distribute them all. We'll have M2GR minus M1 plus M2 R squared alpha equals 1/2 mr squared alpha. Let's get all the alphas together. So we're going to have M2GR equals 1/2 big M R squared alpha plus M1 plus M2 R squared alpha. So this will be 1/2 mr squared plus M1 plus M2 R squared, all times alpha. Let's just take the R squared out. So R squared 1/2 M plus M1 plus M2 alpha equals M2GR. And then we're going to divide this over. So it'll be m2gr over r squared 1/2 m plus m1 plus m2 equals alpha. Let's clean this puppy up a little. So we have m2g over r times half m plus little m plus, or m1 plus m2 all equals alpha. Let's decide how we feel about that, actually. If we had, let's say that the pulley's mass equals 0. So that this would just go away, and we would have m2 over m1 plus m2 times r, which would actually be pretty reasonable for alpha. That's good. Okay. The idea is that by using what we know about forces and what we know about torques, we can actually put them together to figure stuff out. That's a pretty good example. I think that's it, and I'm out.